So we're talking about exponential functions today. Basic exponential function is a number, in this case 2, raised to a variable. So the variable has to be in the exponent for it to be an exponential function. It can be a lot more complicated in this, but the number has to be the base and the variable has to be in the exponent. So this one, 2 to the x, is a doubling function. What that means is if you look at our graph here, whenever we move up one step in x, the y is doubling. So x is going 0, 1, 2, 3, and y is doubling 1, 2, 4, 8, and it will continue to go on 16, 32, 64. So it's increasing at a very high rate of speed, which is why exponential growth is known as something that's growing incredibly fast. If this function were 3 to the x power, it would be growing even faster. So in that case, you might have something more like this. And as you get a higher base number, the graph will get bigger faster. One of the important exponential graphs is 10 to the x. So this is used for a lot of things like decibel levels and Richter scales. So if you look at a Richter scale number, I'm not sure how to spell Richter, but we'll give it a guess. Let's say we have a Richter scale number of 5.2. What that means is it's 10 to the 5.2 power. So that's going to be very high. It's going to be something like more than 100,000, where a 4 would be 10,000. So when they talk about an order of magnitude difference, that's what we're talking about. So that's a really important one. This one is on your calculator. You should have a 10 to the x. Some calculators have a 2 to the x, and some do not. But let's go back to our graph now. There are 3 really important points on this graph. They kind of are the foundation for the graph. 0, 1, anything raised to the 0 power equals 1. So that's something you need to remember. Doesn't matter how complicated it is. If it's raised to the 0 power, it equals 1. And then this, since your variable is the exponent, x is the exponent, this is 2 to the first power. So this is always going to be your base in one of these plain vanilla type functions. And this is another point that's easy to see is -1. So you might recall if you have something like 3 to the -2 power, that's the same thing as 1 over 3 squared, or 1/9. And the same thing's going on here. Here we're having 2 to the -1st power, which is going to be 1/2. So that's what happens when that exponent is a negative. Between those 3 points and the horizontal asymptote of y equals 0, let me get rid of these extras over here. These are kind of the foundation anchors. I'm just going to call them anchors. So it's kind of like knowing the vertex and x-intercepts of a parabola. Those are the main points on a parabola. These are the main points on an exponential function graph. So now we're going to look at the difference between 2 to the x power and 2 to the negative x power. So if you draw the picture of 2 to the x, it looks like what we saw before, something close to that. If you look at 2 to the negative x, it actually looks like this. And that makes sense because this is a reflection across the y-axis. If you remember reflection, whenever you replace x with negative x inside the function, you're reflecting across the y-axis. So this is exponential growth here on the left, and exponential decay on the right. Also what you need to know is this 2 to the negative x, it's kind of a little hard to see, is the same thing as 1/2 to the x power. That's because of our exponent rules. Whenever you have a number that's raised to a negative exponent, it's the same thing as putting it in the other half of the fraction. And that applies here as well. So 2 to the negative x is the same thing as 1/2 to the x power. And those are both instances are going to be an exponential decay situation. So here's our plain vanilla exponential equation. And its important points. Again, that number can be anything. That's why we have a b there to just stand in for a number. It is not a variable, it's a number. And these are its 3 main foundational points, which along with the horizontal asymptote of y = 0, anchor our graph. Sometimes you have a vertical stretching or shrinking going on, and then there's an a out in front of it, another number multiplied by our graph. And then our important points change a little bit in that instance. And you can see they're all just multiplied by the number a, so it's pretty easy. And you want to note what the y-intercept is. And we also have that horizontal asymptote. So those are the basics of the graph of an exponential function and what they do. They're very important. They're used in finance, radioactive decay, pH values, decibel levels, population growth, disease growth, and so very important things to understand. So I hope this was good, and good luck.